Hello everyone, welcome to the channel. In this video, I am going to start with a new topic, that is three-phase system. The previous few videos were on the AC circuits, but all of them were on the single phase circuits. Now what we mean by single phase? The system which generates single alternating voltage. So on the same basis, three-phase system means the system which produces three different alternating voltages. Now we know that for generation of alternating voltage, what we need a magnetic field, or we need a coil or winding which is placed inside the magnetic field. And either of these two should be stationary and second one should be rotating. So if the magnetic field is stationary and coil is rotating, then there is flux cut by the coil and that leads to an induced EMF in the winding. So when we are saying we are three-phase system, it means we need three different windings. All these three windings, they are actually identical. Identical means they have same number of turns, their physical dimensions are also same. And we know that the induced EMF, that is proportional to number of turns and rate of change of flux. It's given by E is equal to minus N d phi by dt. So if the same magnetic field is linking with all the three windings, their number of turns are same, then the maximum value of induced EMF in each of the winding, that will remain same. So when we have three different coils, then in order to understand the generation of three phase, let's consider that we have permanent magnets. Practically permanent magnets are not used because the cost of permanent magnets is very high. Also, they lose their magnetism with time. So it's better to use the electromagnets. So in three-phase system, we have three windings which are identical and they are placed at 120 degree from each other. Because we have 360-degree periphery, they are placed from each other, displaced from each other by 120 degree. Now these three windings can be denoted by A, B, C, phase A, phase B, phase C, or another denotation is RYB. R stands for red phase, Y stands for yellow phase, and B stands for blue phase. R, it will have two ends, R dash, starting end and finishing end, then yellow phase, which will have again two ends. Now this angle is 120 degree. Then blue phase, B and B dash. Now the angle between R and Y is 120, Y and B is 120, and this is also 120. So they are displaced from each other by 120 degrees. The maximum value of induced EMF in these three, that will remain same, but the instantaneous values are different. The instantaneous values, they are dependent upon their position. So if we say that phase R is our reference, then the induced EMF in phase R is given as Em sin omega t. Why sin omega t? Because the flux linkage with these coils, that is dependent upon the position. This one is dependent upon the position. So therefore at one position the flux cut is minimum, that is 0, and corresponding to that induced EMF is 0. With change in angle for anti-clockwise rotation. By after 90 degrees, flux cut is maximum. So that leads to the maximum induced EMF, and then again the EMF will start reducing. And that pattern is followed by all the three phases. So if we say phase R is our reference, then induced EMF is given by EM sin omega t. Phase Y will come to the position of phase R after 120 degrees. So induced EMF in phase Y is given as EM sin omega t minus 120 degree. Because this phase Y is lagging behind this phase R by 120 degree, and similarly the phase B that lags behind the phase R by 240 degrees. So its induced EMF is given as Em sin omega t minus 240 degree. Now these can be represented in the form of waveforms. On this side induced EMF, it will start from 0, 30 degree, 60, 90, 120, 50, 180, 210, 240, 270, 300, 330, 360, 390, then 420, it goes on. On this side we have omega t. Let's say we start with the phase R. So it will have maximum value at 90 degree, 0, 0, then 90 maximum. At 180 its value will be 0. At 270 degree maximum but in negative direction, then going back to 0 at 360 degree. So this is the induced EMF in phase R. Phase B lags behind this by 120 degree. So it means this waveform, it will have 0 value at 120. At 210, first maximum positive value, then 0 over here, moving like this. So it will have the waveform like this. And the blue phase, which is lagging behind the phase R by 240 degree, so it will start from here and it will have maximum positive value at 330 degrees. Negative maximum over here. It was positive at 0 degrees, but that was not the maximum value. So the first phase which is attaining its maximum first positive value, that is phase R, followed by phase Y, then B. So this is a sequence in which the phases are attaining their first positive maximum value, which is known as phase sequence. So the phase sequence for this one is R, Y, B. So this ER can be written as EM angle 0. This one can be written as EM angle minus 120, and this one can be written as EM angle minus 240. Now these can be drawn in the form of phasors. ER, EY 120 degree, and EB 120 degree. All these are angles are 120 degree. And for drawing the phases, we know that we take the anti-clockwise direction. So phase R is the reference, followed by phase Y and then B, or we can have it in the form of ABC also. It can be like EA, EB, EC. Again, all of them are at 120 degree from each other. So the phase sequence is ABC. Now this three-phase system has advantages as compared to the single-phase system. In single phase, the instantaneous power is fluctuating, while in case of three-phase, it's not fluctuating, it's always constant. Also, the output of three-phase systems is more in comparison to the single-phase system. The transmission and distribution of power is also cheaper if we go with the three-phase system in comparison to the single-phase system. And the most important advantage is that three phase motors are more efficient, they have high power factor in comparison to the single phase motors. The size of three phase motors, that is small for the same rating if we compare them with the single phase. Now we have seen that we have three different phases, so there is an induced EMF in each of the phase. Phase R has an induced EMF ER, phase Y EY, phase B EB. So these are the induced EMFs. Now how to connect the load across these? One way is that we connect the load like this. First load is connected across phase R. Second load is connected across phase Y. Third load is connected across phase B. But if we go with this type of connection, then what we need? We need 1, 2, 3, 4, 5, 6. 6 wires for the, or the 6 conductors for transmission and distribution of power, which makes the system much more complicated and expensive. So in order to reduce the number of conductors, these three phases are connected either in star connection or in delta connection. So we can have star connected supply system or we can have the delta connected supply system. Now for star connection means the similar ends are connected at same point. Let's say this is R, this one is R dash, Y, Y dash, B and B dash. The similar ends has to be connected at same points, and then three terminals are available for the connection of load. Now if we just redraw this, it looks like star. ER, EY, sorry, EB. These are the terminals R dash, Y dash, B dash, R, Y, B. So this point, which is the interconnection of these three terminals, that is denoted by N, known as neutral. So this neutral point is available in case of star connection. This side is considered as negative, positive, negative, positive, negative, positive. Now, if we measure the voltage induced in each winding, that is known as phase voltage. Means the potential difference between these two. This is known as phase voltage. Similarly, from here to here, it's phase voltage. This one is also phase voltage. While if we measure the power between any of the two lines, this is known as line voltage. Any pair of terminals, we can say, or any pair of lines, these are the two terminals available from this connection, or between Y and B, again this is line voltage, or between R and B, again this is line voltage. Now what we see over here, that line voltage and phase voltage, they are not same in case of star connection. Line voltage and phase voltage, they are not same. Similarly, we can have line current and phase current. Line current is the current which is flowing through each line, like over here, IR, IY, IB. And the current which is flowing from finishing end to starting end, that is known as phase current. IR is line current, IY is line current, IB is line current. Now IP and IL, they are same. IP and IL, they are same in case of star connection. IL and IP same, VL and PP, they are not same. Now what's the relationship that we need to find out, that I will cover up in the next video. But before moving on to that one, we have to discuss the another connection, which is delta connection. You can say delta connected three phase supply system. So this was star connected three phase supply system. Now let's discuss the delta connected. So again we have three phases, ER, R, R dash, EY, Y, Y dash, EB, B, B dash. Now what, how the delta connections are done? The starting end of first, the finishing end of first is connected with the starting end of second, the finishing end of second is connected with the finishing end of starting end of third. Like R dash is connected with Y, Y dash is connected with B, and B dash is connected with R, and we have three terminals available, R, Y, and B. So if we just redraw the system, that will give us the more clear picture, which will look like a delta. ER, R, and R dash, B, sorry, Y, and Y dash. And from here we have line Y available, from here R available, and third one is B, B dash, and from here we have line B available. So R dash is connected with Y, Y dash is connected with B, and B dash is connected with R. Now this looks like delta. Now the potential difference between any two set of terminals or two lines is line voltage. This is line voltage. This one is also line voltage. And the voltage induced in between the phase is phase voltage. This one is VP. Here we have VP and here we have VP. Now VP is this VP which is across phase R, that is between terminals R and R dash. Similarly, VL is also between R and R dash because R dash and Y they are the same terminals. So it means line voltage and phase voltage they are same in case of delta connection. But if we look at the phase current and line current, now the phase current is from R dash to R, it's IP. Y dash to Y, IP. B dash to B, IP. The current which is flowing in line R is IL, through Y is IL, through B it's IL. So what we see over here that we have three currents flowing over this junction, three currents over this junction and three over this junction. So when we have junctions, it means the currents are no more same. So we have to apply KCL and we have to find out their relationship. So line current and phase current, they are not same. Now what's their relationship? That I will consider in the next video. So the next video will be on driving the relationship between line current and phase current in case of delta connection and line voltage and phase voltage in case of star connection. I hope you will be able to understand the three phase power generation and how they are connected. Thanks for watching the video.